Okay, so ready for this. We're going deep into unsupervised learning today.
Uh-oh.
Yeah,
Yeah.
exactly. It's like where machines learn,
Without a teacher.
right, like without someone saying, hey, you're doing this right, or hey, you're doing this wrong.
Exactly.
Yeah, it's pretty wild. And we're using this lecture by data science professor Ricardo Calix.
Oh, yeah. Professor Calix, his lecture is a really good one for this.
It is. He does a great job of breaking down these kind of complicated ideas.
Absolutely.
So one of the big questions that he starts off with is like, how is unsupervised learning different from the supervised learning that we've talked about before?
Right. Well, the biggest difference is that with supervised learning, you give the computer labeled data.
Right.
And you're saying, okay, here are some inputs,
Yeah.
and here are the outputs.
Right.
And the computer uses that to learn.
Yeah, like a recipe.
Yeah, exactly. It's like, here are the ingredients.
Yeah.
Here's what you do with them.
Mm.
Now you go and bake a cake.
And then you get cake.
Exactly.
Yeah.
Whereas with unsupervised learning,
You just give it the ingredients.
you just give it the ingredients and you're like, figure it out.
Make something. I don't know. Good luck.
Exactly.
So the computer's like experimenting, trying to find patterns.
Yeah. It's all about finding patterns in the data.
In the data itself, wow. So he talks about this idea of clustering.
Right. So clustering is basically,
What is that?
it's a way of grouping data points together that are similar to each other.
Okay.
So imagine you have,
Like think back to school
oh yeah, like in school.
when the teacher would divide the class into groups for like projects or something.
Exactly. And they might group you based on, your skill sets or your interests or,
Sometimes just random.
or totally randomly. That's basically what clustering algorithms are doing.
But without the teacher making the decision, right?
Right, exactly. So instead of a human, it's an algorithm that's saying, okay, these things are alike and these things are alike.
And it might find things connections.
It finds connections we don't see.
That we don't even see, yeah. So like it could group articles about football and data science
Right.
together if it found some like weird connection.
If there's some underlying
Like
latent
yeah.
meaning there in the data.
Latent meaning. I love that. But okay, so how does the machine actually read the data?
Right, because machines,
Because they don't read.
they think in numbers, they don't think in words.
Exactly. So like how do we translate these sentences into something a computer can understand?
So one of the ways that Professor Calix talks about is using this model called bag of words.
Bag of words. Okay.
Yeah. And essentially what you do is you take
They remember I'm talking about that.
each sentence and you just count how many times each word appears in the sentence.
And you turn that into a vector, right?
Yes, exactly. You turn that into a vector.
Okay.
So now you've got this numerical representation.
But that sounds like it creates like really, really long vectors.
Yes, they can be very, very long.
Yeah.
And most of them are going to be zeros.
Right, because most words don't appear in every sentence.
Right. So they're very sparse, very inefficient.
So then how do we make those, how do we go from these long vectors to something that is
More useful.
more meaningful? Yeah.
More compact.
More compact, yeah. What is that?
Well, that's where we get into this idea of embeddings.
Embeddings, okay.
And this is where things start to get really interesting.
Oh, I like where this is going.
Yeah.
This is getting juicy.
And actually, we touched on these when we talked about ChatGPT.
Oh, that's right. Embeddings, I remember.
Yeah. And they're key to how these large language models actually work.
But they're not just counting words, right?
No, they're much more sophisticated than that.
Okay, so how do they actually capture the meaning?
Well, to understand how they work, we need to talk about neural networks.
Neural networks. Okay, I think we need to save that for part 2 of this deep dive.
I think so too, because it's a whole other can of worms.
Exactly. All right, so everyone stick around. We're going to take a break and we'll be right back to keep going with this fascinating topic of unsupervised learning. Don't go anywhere.
Welcome back. So we left off talking about embeddings.
Yes, embeddings. They sound super important.
They are.
And we said they capture meaning, but how?
Well, let's talk about these neural networks.
Okay.
Because they're at the heart of how embeddings are created.
So how do neural networks learn to create these embeddings? Like, walk me through it.
Imagine a network with these different layers.
Okay.
And the first layer,
The input layer.
yeah, the input layer, it takes, in our sentence, represented as a vector.
Like our bag of words vector, right? The long one.
Yes, exactly.
Yeah, okay.
And then that vector, it travels through these
They're
layers.
hidden layers?
Yeah, these hidden layers.
Okay.
And in each layer, the network is transforming the data.
Okay, so it's like each layer is kind of like refining the information.
Yeah, refining it, focusing it, finding the most important features. And then finally, we get to the output layer.
And what happens there?
Well, the output layer tries to predict
Predict what?
the original sentence.
Wait, really?
Yeah,
Why would it predict something it already knows?
that's the trick. By forcing the network to reconstruct the input.
From like a compressed version?
Yeah, we essentially train it to create this compact, meaningful representation.
Which is the embedding.
Exactly.
Wow. So it's like we're squeezing the information down and then stretching it back out again?
And in the process, we create this amazing embedding.
That's wild. So these embeddings, they're not just efficient, they're like maps, right?
Maps, what do you mean?
Well, you said they capture relationships between words.
Ah, yes, that's right.
Like king and queen would be close
Yep,
together.
exactly. And words like king and banana would be far apart.
So it's like we can measure the distance between meanings.
You got it.
Yeah.
That's what's so powerful about embeddings. We can see how concepts are related.
But you can do cool stuff like what? Translate languages?
Yes. Translation, analogy completion, even things like recommending movies you might enjoy.
Whoa. So you're telling me Netflix uses embeddings to know that I like cheesy rom-coms?
Whoa.
That's scary accurate.
It might be part of it.
Okay, I see. So Professor Calix used K-means clustering on those bag of words vectors.
Right.
Would using embeddings change things up?
Big time. With embeddings, you don't need to adjust sentences.
Like he did to make the themes more obvious.
Exactly.
Huh.
Embeddings already encode so much information about the meaning.
So we're basically giving the machine a head start.
A big head start. They can understand the data at a much deeper level.
Embeddings, man, they're like the cheat codes for machine learning.
They're pretty amazing, that's for sure.
But how are they actually made? Like, what happens inside those neural networks?
Well, that's a great question, and it leads us perfectly into the final part of our deep dive.
Okay, because we're going even deeper now.
We're going to the source of the embeddings.
All right. Everyone stick with us as we unravel the secrets of how these incredible embeddings are created. This is going to be good. Okay, so we're back and ready to uncover the secrets behind these embeddings.
Let's do it.
We talked about autoencoders and neural networks.
Right.
But, I'm still kind of fuzzy on how it works with text.
Okay, well, think about how we start.
We start with that bag of words,
Exactly.
turning the sentence into a vector.
A long vector.
Right, but those were sparse and not very efficient
Yeah, we need something better.
to capture all that meaning.
Right, and that's where the neural network magic happens.
Okay, so explain the magic. How do they create those dense embeddings?
Picture a network with all these layers.
Like onions?
Kind of. Each layer processes the information.
So it's like each layer is getting closer and closer to the core meaning.
Exactly. It's finding the most important features.
And then at the end,
We have the output layer.
what does that do?
It tries to predict
Predict what?
the original sentence.
Wait, but it already has the sentence.
I know. It sounds crazy.
Wait, why?
By forcing the network to reconstruct the sentence from this compressed representation, we force it to create an embedding that captures the most important information.
Like squeezing all the juice out of the sentence?
Yeah, and only keeping the good stuff.
That's pretty wild. But how do we know if it's a good embedding? Like, what's the test?
We use different metrics.
Like what?
Well, for example, if the embedding for king is closer to queen than it is to banana, that's a good sign.
Makes sense.
It means the embeddings are capturing semantic relationships.
So we're basically checking if the machine is learning language like we do.
Exactly. We want to see if the embeddings reflect our understanding of the world.
And then we can use these embeddings to do all sorts of cool things. Right?
Absolutely. We can do things like translate languages.
I remember you said Netflix even uses them to recommend movies.
Right. Embeddings are everywhere.
Wow, it's mind-blowing to think that these mathematical representations can capture so much meaning.
It really is.
And it all started with Professor Calix's lecture.
He laid the groundwork for understanding these complex ideas.
Well, this deep dive has been a wild ride through the world of unsupervised learning, from clustering to embeddings.
We've covered a lot of ground.
And it's amazing to see how these techniques are shaping the future of AI.
Absolutely. And it's just the beginning.
So keep learning, keep exploring, and who knows what incredible discoveries you might make.
Until next time.
And thanks for joining us for this deep dive into unsupervised learning.